By having the experience with the bode diagrams of all the problems we have seen, let us summarize the stability analysis in the bode plot. Now, one typical system having a magnitude and phase plot like this. So, the magnitude plot, the reference line is 0 dB. In phase plot, the reference line is minus 180 degrees. So, in magnitude plot, I have the magnitude plot like this, which is crossing the 0 dB at the point x, for example, that is omega gc. Now, similarly, phase plot is crossing the minus 180 degrees at point y, that is omega pc. Now, where omega gc is here, the omega pc is here. Now, for this particular system, omega gc is less than the omega pc. So, we are varying from lower frequency to higher frequency. So, initially we will get omega gc, then after that we are getting omega pc, which means omega gc is less than omega pc. The second, if you observe at this omega gc, then I can look at what will be the phi gc. It is not the value that is important, where the phi gc is. Phi gc is the above 180 degrees line or below 180 degrees line. Now it is above 180 degrees line. When you have above 180 degrees line, then phase margin is going to be positive, because that value is negatively less than the 180 degrees. Therefore, so when I say 180 plus phi gc, the phase margin is going to be positive. So you will get phase margin positive if at all phi gc is above minus 180 degrees line. Similarly, at omega pc, when you look at what will be the MPC. So now in this case, the MPC, again it is not the value, the MPC is below the 0 dB line, we are getting the negative value. So when MPC is below a 0 dB line, then gain margin is going to be positive. So when you have gain margin positive, phase margin positive, then corresponding closed loop system is a stable system. Now what are the conditions from this? We can say for a stable system, omega gc must be less than omega pc, and phi gc point must be above the 180 degrees line, and MPC point should be the below the 0 dB line, and phase margin should be positive and gain margin should be positive. So these are the conditions for stable system. Similarly, look at the second one. In the second one, so again I have the magnitude and phase plots, but there is small change in this case, where your omega pc is here and omega gc is there. Means, so omega pc is less than omega gc, or I can say omega gc is greater than omega pc. Then where will be the phi gc value? Phi gc is below 180 degrees and MPC is above 0 dB line, just opposite to this. So when phi gc is below 180 degrees, which means phi gc value negatively more than 180 degrees, therefore phase margin is going to be negative. Similarly, your MPC value is above 0 dB, which is positive, but gain margin is minus MPC dB, therefore gain margin is negative. Then what are the conditions for unstable system? If at all, if you have gain crossover frequency is greater than phase crossover frequency, and your phi gc point is below 180 degrees line, and your MPC point is above 0 dB line, the corresponding gain margin is negative, phase margin is negative, the closed loop system is unstable. Take the third case, a typical case, where, so I have magnitude plot and phase plot. So magnitude plot is crossing the 0 dB line here, and phase plot is also crossing 0 dB line. Both are at same frequencies, which means my omega gc is equal to omega pc. Then what is the corresponding phi gc is 180 degrees. Therefore, what is the phase margin is 0 degrees. Your phi gc is minus 180 degrees, 180 minus 180 will be 0. Similarly, so when you look at what will be the MPC, MPC is 0 dB. Therefore, gain margin is also 0. So when you have such kind of system, then the system is called, closed loop system is called marginally stable system or critically stable system. The system response will have continuous oscillations, or we can also call it is oscillatory system. So this system is very important, because whenever you have system, we need to analyze at this case. So when you have a clear vision at the critically stable condition, then we are much aware of that when you are designing. system should not reach to that stage. So what are the condition for marginally stable? Your gain crossover frequency, phase crossover frequency should be same, and phi GC should be minus 180 degrees and MPC should be 0 dB, and therefore the corresponding phase margin will be 0 degrees and gain margin will be 0 dB. So these are the condition for marginally stable system. So using a Bode diagram, we can find out the error constants of the system. So we know the error constants are Kp, Kv, Ka. Kp is a positional error constant, Kv is velocity error constant, and Ka is acceleration error constant. And Kp is for the step input, and Kv is for the ramp input, and Ka is for the parabolic input. So now they will get the corresponding Kp value when you have such inputs. But Kp, Kv, Ka we can find out from the magnitude plot of the Bode diagram. So how to find that? Whenever you have a type 0 system, then you will have Kp as 20 log K. So you know what will be the K value of the system. The Kp directly we can take it as 20 log K. Because for type 0 system, initial slope will be 0 dB. So 0 dB it will be like this. So you know what is the K value, then we can find out the Kp as 20 log K. So when you take a type 1 system, so type 1 system is one pole in the denominator, therefore the slope is decreasing. So when slope is decreasing, then it is going to cross the 0 dB line at omega. Therefore your velocity error constant is where the 0 dB line, where that magnitude plot crossing the 0 dB line, that omega is Kv. So Kv directly we can write it as omega. Then Ka for a type 2 system it is omega square. So we can look at these three and you can directly find out what is Kp, Kv, Ka of the system depending upon their type 0, type 1 and type 2.